Hi, good morning, class. Um, how are you today? I hope you were not bored waiting for me. I had some problems with the connections, but now it's a little okay. Yes, I have received your messages, and as I was checking the attendance, the first one was Mela Grace. Then we had also Eugene, Marsden, Jay, Jezreel, Rena May. Um, we have Hosni, we have Joven, we have David Paul, we have Era. So can you hear me? By the way, can you comment and if the sound is okay or not? We have GJ also. Please comment if you can hear me or not. Thank you so much, David Paul. So let me start with the lecture now, and I will go faster today. We will not be proving so much um, with the mathematics of electrodynamics because we want to start as soon as possible the second chapter, which is really the meat of electrodynamics. The first chapter, this one we're discussing about, are just mathematical methods that we're going to use as we approach the electrodynamics problems. Although this is not necessary, but I feel that I had to do this because um, you may have forgotten some of your lectures before. So in the previous lecture, we discussed some of them, and then we will continue for this lecture. And hopefully, by the next lecture, we will be finishing this chapter, and the next lecture will be really the electrodynamics um, lecture, the meat of our course. Um, Again, I'm using the Introduction to Electrodynamics by David J. Griffiths. I have the old edition, but if you have some resources, some financial resources, please buy this book. This is really worth it. So from the previous lecture, we said that the dot product of two vectors, these are vectors. Please remember that these are vectors. uh, Vectors, you can only dot two vectors, not a scalar. You can multiply a scalar to a vector, but you cannot dot a scalar to a vector. You can only dot a vector to a vector. So here you have x dot x, y dot y, and z dot equals 1. And then when you dot a vector to a perpendicular vector, that's supposed to be 0, just like what happens here. X dot y, x dot z, y dot z are 0 because they are mutually perpendicular, meaning they're perpendicular relative to each other. You can also reverse this y dot x because they are commutative. So if you have a vector A dotted to a vector B, use the components method. For here, you have a dot b is equal to ax bx plus ay by plus az bz. And the magnitude, of course, you're dotting a vector to itself. That's just ax squared, ay plus ay squared plus az squared. And then we also had cross product. These are cross product of two unit vectors. So, cross product, the magnitude of the cross product is the product of the magnitudes of the two vectors times sine theta. In this case, x cross x is a cross product of a vector to itself. A vector to itself, meaning you're crossing a vector, the same vector to that same vector, and the angle between them is 0. So sine 0 is 0. So you're crossing a vector to itself, like this, for example, y dot y, y cross y, z cross z. That's all equal to 0 because the angle between them is 0. For um, crossing a perpendicular vector to another, is depends, the direction will depend on your right hand. So if you're cross x to y, that's z, but the reverse of that, y cross, oh, x cross y is equal to z, but the reverse of that, y cross x, would be negative z. So it follows, no? So you have an order here, x, y, z. So the product of x, y is z. And then y, z, x, then z, x, y. You have that order. X, y, z, y, z, x, and z, x, y. So if you have a cross product of two vectors, a and b, you can expand a to its components, cross b to its components. Then if you distribute each of these, and you will come across with x cross x, x cross y, or y cross x, then you'll be able to get this expression. Remember, the a cross b, this is a cross product or a vector product. You have directions here. You have directions x, y, and z. And the components are given by this. The x component is given by that. Look, the x component includes only y and z. Z and y. For the y component, the component term is composed only of z and bx, or z and x, or x and z. And look at the z components. It's only composed of x and y and x. This is for a cross b. And for a dot b, you only have this. No directions for that product. There's no direction for that product. Okay. So um, I am looking at your chats, and uh, if there's any problem, please chat me the the problem. So A cross B can actually be written in determinant form. So this is your A cross B. So if you get the determinant of this, you write this first, like this one here. This one will be here. This one. And this Y will be here. And this Z will be here. And then you cover this, you cover this, and cover that for X component. And then you only have YBZ minus YBZ, AYBZ, I mean, AYBZ minus BY or AZBY. So that's how you get the first component. For the second component, it's supposed to be negative here, but you are interchanging this. So it's supposed to be negative Y. This one here, it's supposedly negative Y. And then you cover this one, you cover that one. You have AXBZ. You cross AXBZ, you multiply that, minus B or AZBX here. But the negative sign here would be compensating with the order of the fact of the terms here. So that's now AZBY minus AXBC. So that's for the second term. And then for the third term, you have Z. And then the terms here, you have to cover that one. You have AXBY minus AYBX. So that's how you get the cross product using matrices. So we also had a scalar triple product. Scalar triple product, you can write that in matrix form like this. So instead of the instead of the AX, instead of the X hat here, you can write AX hat here with in as replacement to the X hat AX. And then for AX you can write BX. So you can write BX here, and for BX you can write CX. So here, for example. So that's the scalar triple product. Look at the scalar triple product. The X hat, the Y hat, and the Z hat is replaced by this. They are not directions, they are components, magnitude of the components. So this one is a scalar triple product. That means it has no direction. For the vector triple product, you have direction. Triple product is written here. So vector product means it has direction because it's a vector. So here you have A dot C is a scalar product. So it is a scalar multiplied to a vector. And A dot B is also a scalar multiplied to a vector. So the difference of two vectors is a vector. So it's a vector. Then we also had position vectors. So R is the position of a particle from the origin to the particle itself. So from the origin, you have here going to the point. So the position would be x here, the x position, the location of the point, and then you also have a y component of the position, which is this. This is the y component, and then you also have the z component, here. So the total displacement from the origin would be this vector. This is the sum of the vector, the resultant position. So its component is written like this. And the magnitude of that would just be the square root of x squared plus y squared plus z squared, the generalized Pythagorean theorem. Remember, R has direction, x, y, and z, but the magnitude has no direction. Remember, this is the magnitude, but the vector has a magnitude and a direction. So don't forget the direction. This is how you formally write the vector with its components. Now, the unit vector is pointing radially outward. By convenience, we write the vector, the r vector or the position vector, to be pointing radially outward. We set that convenience, and um, and it's positive always if it points outward. The unit vector r associated with this position, um, there is a unit vector r here. This is parallel to r, and that is defined as r divided by its magnitude. So x over this quantity, x times x hat over this quantity, y over this quantity on the y direction, and you have z over this quantity on the z direction. So if you move from a point to another point by a small amount, like in this case, you move very little from your position, initial position to a final position, but only very small or infinitesimal, very very small, very very tiny. Um, you're now on a position from x, y, z to x plus dx, y plus dy, and z plus dz. You're moving a small portion, very small. Then you have incurred a displacement vector dl. Uh, the dl here is written as this. dl is dx x hat, dy y hat, and dz z hat. So this is also a vector, and that is parallel to the position vector. No, I'm sorry. This is parallel to the vector connecting xyz, um, xyz to x plus dy plus dz. Okay, I'm back. Sorry. Um, Here you have, again, I'd like to repeat that the dl is parallel to the position, to the vector, or it is the vector that connects xyz to x plus dx, y plus dy, z plus dz. Okay. Or it is the vector that it is parallel to the vector that connects to uh, parallel to the vector that connects xy, xyz to x plus dx, x plus dx, y plus dy, z plus dz. I hope you're not confused. Um, we also encounter separation vector. We discussed about this in the previous lecture. You have a position r. This is the origin, and then this is your source point. This source point could be a charge that is um, emanating some fields, no, or disposing some fields, and then you measure that field at this point. We call this point field position. So the position of a source point is r prime, and then the position where you are detecting or measuring the field is r. So there's a position, or we call this a separation vector from this point to this point. We call that the scripted r, or the separation vector. This is the difference of the field point and the source point, and we write it like this: the difference of the source position to, I mean, the difference of the field point minus the source position. So here you have this scripted R. The magnitude would just be given by this, and the unit vector is of course this is the unit vector associated with this vector. This is just R, the scripted R divided by the magnitude of the scripted R, or you can write it like this or like that, no? Expanded form. And then if you use the Cartesian coordinates, um, the scripted R would just be this. And of course, when you get the magnitude, you just have to square the components. Forget about the direction. So these are just the components. This one would just be equal to that. And then this one would just be equal. Um, This one will just be equal to that, and this one will just be um, equal to that. Forget about this. Forget about the direction in the magnitude. Okay. So this one, forget about the direction in the magnitude. The magnitude is a scalar quantity. So you can also write this expression in terms of the Cartesian coordinates like this one. So we now go to the transformation of vectors. Last time we transformed a vector. We have a three-dimensional vector here. We rotate in the x-axis some angle phi. So we rotate the x-axis with some angle phi. So as a consequence of that rotation, we change the y-coordinate to y bar, and then the z-coordinate to z bar. So there's now an angle phi here. This angle is equal to this angle phi. So there's so the phi, the original angle phi of the vector, I mean the original angle theta of the vector A to y. So this is the original angle of A to y. You have now there's now a change in the angle, and we call that angle to be consistent theta bar. And theta bar is just equal to theta minus phi. Theta bar is theta minus phi. So your AY, A cosine theta, becomes AY bar in the new coordinate system. That's A cosine theta bar. So this, you can expand this by using some trigonometric identities. You can expand that. This one is equivalent to this, and you can have this expression eventually. And then for AZ, that's AZ bar would be A sine theta bar. So your A sine theta minus phi, you finally will get this expression for AZ. And then you can write this in matrix form. The AY here will just be this one, and your AZ would just be this one. So AY, you can write this as a vector here, a column vector. Yeah, this is one as a first rank tensor, but don't confuse yourself with tensor. We'll just call this for now a vector. So this is AY, AZ. So if you multiply AY cosine theta, that's this one. And then you multiply AZ sine phi, sorry. This is this one. And you multiply negative AY to the negative sine phi. This is this one. And then you multiply AZ, AZ cosine phi. That is just this one. So everything you can, for this, you can always convert to matrix form. For in general, if you have a three-dimensional vector, that's you'll be multiplying matrix in 3 by 3. The dimensions of the matrix would be 3 by 3. So AX would be multiplied to here, AX will be multiplied here, and AY will be multiplied here, and that one will give you AX bar. This one. And compactly, you can write it in summation form. So instead of writing the matrix, you can write it like that. For the rotation about the x-axis, because the x for the x-axis rotation about the x-axis, the ax bar would just be equal to ax. So therefore, this must be equal to 1. Rx x must be equal to 1, and this one must be equal to 0. Yes, because ax bar would just be equal to ax. And rxy, of course, this is supposed to be symmetric. I mean, not really symmetric, but this one should be also 0, because ax, the ay does not contain a component in the x, so this is supposed to be 0 also, and this one is also 0 because az bar does not have an x component. So this is the matrix. You can write this as 1 0 0 0 0 cosine phi, sine phi, negative sine phi, cosine phi. We will do more of this in the curvilinear coordinate system. So for the second rank tensor, you, of course, this has an equivalent matrix, and the tensor TKL is a 3 by 3 matrix, and it has 9 components. The 3 by 3 matrix will be operated by first by this one and then by this one. The two R's here just look like this also, but they may have different components. So again, a vector is a rank 1 tensor, and a scalar is a rank 0 tensor. Now we will go to differential calculus, and we will first start with ordinary derivatives. So in your lectures in calculus, you're always given a function, and then you're going to find the derivative of that function with respect to the variable. So if this function is dependent on variable x, then you can get the derivative of that with respect to x here. This is the derivative of x with respect to x, or formally, you can write that as this one. So for example, if you have a function f of x equals to x cubed, for example, and you get the derivative with the first derivative with respect to x, that's just 3x squared dx. So 3x squared dx, that's the first order derivative. So the derivative means if x is changed by an amount dx, if x is changed by an amount dx, or if the variable is changed by an amount, by a very tiny or infinitesimal amount, then f changes by an amount df. This is what the derivative is all about. This one, the df over dx, is also the slope of the tangent line to the curve, represented by f. F is a function, it is a curve in the xy plane, or xf plane. So that is a curve here. So if you want to get the slope of the tangent line here, you just draw a tangent line here. The slope of this tangent line is the derivative of f with respect to x. This one. The derivative if you look at this equation, the derivative is the proportionality factor, but this is not necessarily constant. The proportionality factor is the slope of the tangent line. So the slope here at this point, so the line would be like that. So the slope here is smaller, but the slope here is would be steeper, would be higher. This one you have a small slope and then you go to a higher slope. Look at this figures. Um, Looking at this figure here, you have a slowly varying slope, slowly varying derivative as you go from 0 to x. But here, your slope comes from 0 or very small number to very high in this graph. So um, you can get the behavior of the slopes here by getting the derivative. So geometrically, the derivative is the slope of the tangent lines of the graph x versus x. So I think that you know that in your calculus class. Now we go to the gradient. In this case, you're now dealing with functions of multiple variables. In this case, we will start with 3 variables. So if you have a function with 3 variables, say for example, the temperature in a room, you have a function of the temperature. So say you measure one point in the room here, and then you measure the temperature, and then to another point, you measure another temperature here at this a different point, and then in other points. Then you can um, more or less formulate the function for the temperature. So of course, this is a continuous function. So how do we generalize the derivative? Because from one point to another point, you are changing not only x, not only y, or not only z, but all of the 3. So what you do is to generalize the derivative, you have to do this. So you are now changing dt from t. You change by dt. If you change the position from x, y, z to x plus dx, y plus dy, plus and z plus dz. So there's a change in position. But look, you are differentiating the x here only, and you are differentiating the the t by y only, and you are differentiating the t function by z only. And by the way, it looks different. Look at this. You're using the derivative here with a letter d, and here you're using a partial derivative. You're using a partial derivative. You're using a partial derivative because t is a multiple variable or a multi-variable function. You have a function which has a variable of x, y, and z. So you only, here in this case, you only get the derivative with respect to x, treating y and z to be constant. Here you're getting the derivative with respect to y, treating x and z to be constant. And by the same argument here, you're just differentiating t with respect to z. You can only use partial derivative if you're getting the derivative with respect to a single variable. Uh, you're only using partial derivative if you're getting the derivative of a multivariable function with respect to a single variable. In this case, x. In this case, y. In this case, z. But then you have to multiply with dx, dy, and dz. And here you get you use d because this is a total derivative. Of course, and same here, and the same here. Only this one is partial derivative. Although the operator d, or the operator derivative, has the same function as the partial derivative. This just represents that you are differentiating a function of multivariables, in more than two variables, with respect to a single variable. So that's just the difference between partial derivatives and total derivatives. But the operation is still the same. So, for example, if t is equal to x cubed y squared, if you get the derivative of, anyway, let's go to an example later. So you can write this. You can write this expression. You can convert this expression into a dot product here. So if you do the dot product, look, you can write this one as this one, as that one. So if you do the dot product, if you do the dot product of this, you can get this. Okay. But then for notational simplicity, we define this. We define this we define this to be the gradient of t. And this gradient of t is a vector. This is a vector x, y. It has a direction x, y, x hat, y hat, z hat. And then, of course, this is the dl we defined earlier. No? This is the dl. Yeah, this is the dl. So you can write dt. Again, this is just rewritten. Dt is equal to that, and then this is just the gradient of t, and this is just dotted to dl. So the gradient of t is again this one, or you can even factor out t outside. So you will see that later. The gradient of t is a vector quantity with three components. And this is a generalized derivative of t. Generalized derivative, the gradient. So equation 35, this one, equation 1.35 is the three-dimensional version of, this is the one-dimensional, but this is the three-dimensional version of the derivative. I mean this. Sorry. The three-dimensional version of the derivative. This one is represented by the gradient. This is the derivative of f with respect to x, but f here is a single variable, whereas here your t is a multivariable function. And then your dl is not simple, it's now with direction. And you use the dot product instead. Here you are just multiplying. Here you are dotting. And that product is different from just multiplying. What is the geometrical interpretation of a gradient? So this is your gradient here. And of course you can write the gradient. This is the gradient. I mean, not the gradient, the total derivative of t, and this is the gradient dotted to a dl. So of course, by that product, you can get the magnitude of gradient of t times dl. cosine theta. This is the angle between a gradient of t and dl. Now, um, if the magnitude dl is fixed and you search around in various direction, you search around in various direction. So you are varying theta. The maximum change in t occurs when theta is equal to 0, because cosine 0 is equal to 1. So if theta is 0, cosine 0 is equal to 1, that is the maximum derivative of t. So dt is greatest when the motion is in the same direction as or the gradient points in the direction of maximum increase of function t. So the direction is pointing to the maximum increase of function t. And again, as a definition of a derivative, the magnitude of the gradient of t is the slope or rate of increase along this maximal direction. So if you find that the angle is 0, then that is the direction of the gradient of t. This is the gradient of t, represented by that. So if you're in a mountain where there are so many curves, three-dimensional curves, you just find um, uh, the theta that is 0, that will give you the maximum or the greatest derivative. That would be the direction of your gradient t. So now imagine yourself standing on a hillside. Then you look all around you. If you find the direction of the steepest ascent, that is the direction of the gradient. Steepest ascent, going up. Then you can measure the slope in the direction, or the rise over the run. That is the magnitude of the gradient. That is the magnitude of the gradient. I know it's still hard for you to imagine this, but if you think of this every now and then, you'll be able to get what I mean. So, like in equation 137, the direction of maximum descent is opposite to the direction of the maximum ascent. And if theta is equal to 90, the slope is perpendicular. I mean, the gradient or the slope is perpendicular to the contour line. So if you have a contour line, the slope is perpendicular to that. So I hope you can ask more of these questions in more of this similar questions in our Molly room. If you don't understand yet the explanation, but because it's hard to imagine 2 or 3-dimensional curves, or that's what you call a surface. So again, we do the derivative to get the maximum or minimum of a function by letting the derivative of that function go to 0. And in one dimension, if you have f of x and you want to find the maximum or minimum or the extremum of that function, you get the derivative of that function with respect to the variable in which it is dependent. So for example, f derivative of f with respect to x, you set that equal to 0, and you'll be able to find x or some x's, and then you substitute those x to the function, you will get the maximum or the minimum or the extremum. So by doing this or setting the gradient equal to 0 at xyz, then uh, dt is equal to 0 for small displacements about the point xyz. So by setting that equal to 0, you'll be able to get the value of x, y, and z. You'll be able to get the x, y, and z. And if you substitute that, to t, x, y, z, then you'll be able to get the maximum, the minimum, or a saddle point or a shoulder. The maximum, so if you have a mountain, the maximum would be the summit. And if you have a valley, I mean, a mountain like that, two mountains. Here are two mountains, and the the lowest point would be the valley. And then you also have a saddle point or a shoulder like this. Here, the slope on the shoulder is also equal to 0. So you can have you can review your calculus and see what I mean about maximum, minimum, and saddle point. That's they have clearer pictures on single variables. Now, um, yeah, if you want to look at the extrema, you just have to equate the gradient to 0. So here's an example. Find the gradient of r, which is the position of which is the magnitude of the position vector. Find the gradient of r given by this equation, the magnitude of the position vector. So the gradient of r will just be using the formula. You just do this. Use the formula here. So r. So here you have what is the derivative, partial derivative of r with respect to x. It will just be given by this, and the partial derivative of r with respect to y will just be this, and the partial of r with respect to z will just be this. Note that it has direction x, y, and z. It is a vector. And so the gradient of r is just equal to this, which is just equal to r over r, which is just equal to the unit vector r. So the gradient of r, which is the position vector, is a vector, the unit vector r. Okay. So you can imagine that example, and then when realization comes and you have some questions, just post it in our Molly room or in our Google room. Now, let's talk more about the operator del. This is what you call the del operator. Read that as del. This one. The gradient operator is called del, operating on a scalar t. As I've said earlier, you can factor out t here. You can distribute the t or you can factor out t. This one is the gradient of t. So this is the gradient, and this is your function t. The del in the usual sense is not a vector and it is without specific meaning, but um, it can imitate the vector. Um, it only means derivative, actually. It only means derivative, the del, but it is a generalized derivative. So when you operate this to a function t, meaning you are getting all the derivatives of the variables where t is independent. Um, so the del is the instruction to differentiate the function that follows it. So del is a vector operator that acts upon t, not a vector that is multiplied to t. Vector that you know. Del is a vector operator that acts upon t, not a vector that is multiplied to t, acts upon. This del mimics the behavior of an ordinary vector. And let's look at the difference between the multiplications of vectors um, and multiplications of the gradient, no, to a function. So for example, if you have a vector A, you multiply a scalar A. This is a vector A multiplied to a scalar A, or this is just equal to the scalar A multiplied to vector A. In this case, the del is acting on a function t. This is called the gradient. And here, but here you can commute. Here, you cannot commute. This has no meaning. T times del t del has no meaning unless you put a function next to the del here. If you put a function here, then that has meaning. But these two doesn't have meaning. You have a dot product with vector b for two ordinary vectors. This is a dot b. This is just equal to b dot a. This is equal to for the dot product of vector function v. You have del dot v. This is the divergence of v, but this is not equal to v dot del. This has no meaning unless you put a function here. Again, you have to put a function on this side. For the cross product, this is a cross b. This is equal to negative b cross a. For the cross product of vector function v, so del cross v, this is the curl of v. Remember, this is this is how you read this divergence of v, and this is how you read this curl of v. This is not equal to v cross curl, so you cannot commute them unless this has no meaning unless you put a function here. So divergence. So this is how um, you get the divergence of a vector function. So if in general your v will look your del will look like this, and your v will look like this. You have a vector function here, which has components in the x, y, z direction. So you can dot this. This is the divergence of v. So it has become a simple definition of that. So we can. This is the divergence. So of course, if you have a source point here, a charge, the electric field would be diverging from that point. You have it's diverging from the point, the fields. This has no divergence. Why? This has no divergence because the vectors here are the same. They're all the same. It doesn't change. But here it is diverging because the vectors, the length of the vectors are diverging. So at some point from the source, the vector has a is change at any point. So like here, it's the value of the vector is smaller here, and then in this case you have larger, and then it becomes large. So it's getting bigger. So there's change as from one point to other points. This also changing from one point to, but here it seems to be constant anywhere. So there's no divergence. That's the meaning of divergence. So your this is the divergence. This is the measure of divergence of v from a point or from a line, for example. So there's an illustration for that. Imagine standing on the edge of a pond, sprinkle some sawdust. If you sprinkle some sawdust, if you know that, or powder on a pond, if you put some powder, if they spread, if you want to measure the divergence, if they spread, you just get the del of the vector. So that's what you call um, positive divergence. But if you have some particles in a pond and they are moving towards each other, like lumping towards each other, that's called negative divergence. So for example, if you're uh, pouring out water from a faucet, so the water falls down from a faucet and it diverges on the surface, that's what you call um, divergence of the water. So that's the geometrical interpretation of divergence. And then if you have a sink, if the water will converge in the sink, that's what you call negative divergence. So it's positive negative divergence. Um, Positive divergence is like a faucet, and negative divergence is like a drain or a sink. So in given some functions, here, for example, you have VA equals R, which is the position vector here. You can get the divergence of this by doing this and doing that. So this is just the divergence of VA will just be the partial derivative of x with this one is this one, and then y would just be that one, and the z would just be this one. Look at this expression. This is the definition of divergence. So if you want to get the divergence um, of VA, that's just equal to 3. Because partial derivative with respect to x is 1. Partial derivative of y with respect to y is 1. Partial derivative of z with respect to z is 1. So this is equal to 3. For b, for this vector, b, vb, supposed to be in boldface. You have z. So the divergence of vb would just be, it has 0 x, 0 component x, and 0 component for y, but it has 1 as a component for z. So what's the derivative of 1 with respect to z? That's also equal to 0. So everything is 0. For vc, um, it has a 0 component on x, 0 component on y, and z component on z. So this is 0, this is 0, this is 1. The partial derivative of z with respect to z is 1. This is 1. So that's an example. I hope you can, that's easy for you to understand. And then we have the curl. Um, this one is the definition of the curl here. So it's just the same as the matrix before. And so you can find, by doing this, you can get this expression. So this is the curl. That is the curl. Note that the curl is a vector function. Note that the curl of a vector function is also a vector function. It's also a vector because it has direction. A scalar cannot have a curl. Why? A scalar does not have a curl because it cannot. It doesn't have direction. You cannot curl a scalar. You cannot have a divergence also of a scalar because that does not have a direction. So you can only get um, the divergence of a vector. I mean divergence of a vector and curl of a vector. You cannot get the divergence or a curl of a scalar. So this is also the meaning of curl. So you if you have if you have a vector that's curling a point, or like a whirlpool, that's a curl. This one also is a curl, isn't it? Although this is kind of straight arrows, but on the opposite side you have this in this direction going to that, and on this side you have this direction. That's also a curl. That's the geometrical interpretation of curl. For divergence, you have to. This is it's not curling. It's just diverging away or converging to the point chart. But for the curl, it is like um, what you call it, revolving around the point. So this is what you mean by the curl. So um, for this example, you have a vector VA given by this. Um, if you get the curl of VA, so again, use this formula. You just substitute for using this formula before. You have this. The A here is your del, so the A is replaced by this. And your VA, your X component is negative Y, and your Y component is X, but your Z component is 0, so you can get the curl of this. The curl of VA, which is equal to that, is equal to 2 Z hat. So it has direction. It has direction. So this function is on the XY plane. So the curl on the XY plane will be Z. That's perpendicular to the XY plane. Here, for VB, you have this is VB. You can again use the formula, substitute the components of the VB here. You will get also a Z. It looks like this. The curl on the y-axis. The curl on the y-axis is like going. It's also in the Z direction. This one, the first one here is also in the Z direction. You just use your right hand to determine the direction of everything. Um, the cross product, the curl, everything. And then we have the rules on derivatives. You know all about this. The sum rule, you know that multiplying by a constant, you can take out the constant from the derivative. And then the product rule, here, you get the derivative of the second. You take f first out of the derivative, and then you sum uh, this with the derivative of f times g. So this is, you know these rules. And also for the quotient, you know that rule. In similar fashion, you also have rules for vector derivatives. No? This one, for the sum, of course, we know this already. And we know this also. You can distribute the del to the vector. And here, the del of kf will just be k. K is a constant. You can take that out of the del. So you're only operating del on a function. This one is also, this k is also a scalar, so you can put that out of the del. This one is also in the same argument, only that this is a cross product. This one is a dot product. So remember, that product always gives you scalar, and vector product always gives you a vector. It has direction. So these are the rules. So for gradients, you have this rule. So it's the same thing. It's just generalized derivative, no, that you're using here. So this is the same thing. This one, you can prove these identities. You can prove by component method. You can prove this by component method by if you expand this by component and you expand this by component, if they're equal, then they're the same. You also have this rule. This one, you have this rule also. So you can see that. And for the triple derivative, I mean triple product, but in this case uh, you have a del. So that would be, this is the backup rule, no? So for the curls, you can also have this identity. You also have this identity. So in component form, you can prove this. So the del will just be this one. If you dot f ax, f ay, and f az, so you you will be able to show that this one is equal to this one. So let's not prove that here. We'll just introduce that to you again because it's already taken in your mathematical physics before. And for the quotient rule, you have also these rules, which are very similar to these um, rules. So that one is the last slide for today. I will not pressure you. Just prove it yourself. I will not collect the proof, but I hope that you will do it. You will have the passion to do the mathematical things. And if you cannot do it, ask your classmates or ask me in our Molly room. By the way, if you know the answer, if somebody asks for help in the Molly room or in the Google Classroom, if somebody asks for help and you know the answer, please tell your classmate that this is how you do it. Um, Also, as a community, we can discuss together. But of course, I also have other classes. I also prepare some other things aside from my classes. So I cannot answer immediately your inquiries in the Molly classroom. But if your classmate knows about the problem, and if you can answer that, please do so, because that's way of helping your classmates learn also. All our goal is for us to be able to learn the same thing in the same interpretation that the book is giving us. So that's help bayanihan. That's why we're helping each other. That's a part of our culture, bayanihan. Help your classmates. Of course, by helping your classmates, you have helped me ease some of the things that I need to do for you. So if you could help, please help in our Molly room or in our Google Classroom. So that's all for today. We'll be continuing this. I hope I will have no problem in the next time. I will have no problem with the connection by Monday. So thank you so much for listening, and I will review your chats after the lectures. Thank you. See you.